Hello, and welcome to ML with Philip. If you're new to my channel, this is a channel where I make educational videos about machine learning and artificial intelligence. This is the third video in my natural language processing series, where we focus on building recurrent neural networks from scratch. In this video, we are going to learn how to create a neural network that is going to be able to translate sentences from French to English. This is a very interesting problem because it is a sequence to sequence type problem. So we actually have a sequence of French words and we're going to have to try and translate it to a sequence of English words. In this video, we're going to take everything that we learned in the first two videos and we're going to put it all together to tackle this more complex problem. So we're going to create an encoder decoder network. What that means basically is we're going to have an encoder, which is simply an RNN that is going to be responsible for taking in the French sentence input and encoding it as useful information. And then we're going to have a decoder, which is going to also be another RNN, and it's going to be responsible for generating the English sentence output word by word, and it's going to take the encoded information from the decoder, which contains all of the context and the content that was contained in the input French language sentence. These two are going to work together to form the basis of our architecture, and they're going to result in a neural network that is going to be able to take a French sentence and learn how to generate the English sentence translation. This is going to be a great video, so I'm excited to get into it and I hope that you enjoy. Alright guys, so before we dig into the code, I want to draw some diagrams so that we better understand what the architecture of our neural network looks like. Okay, so let's start with drawing a diagram of our encoder. Let's give it a sample input and output that we'd like to translate. So the sentence that we'd like to translate is I love dogs. In French, that is Je aime les chiens. And in English, this is I love dogs. Okay, so the first thing that we can notice is that je aime, if you're not familiar with the French language, this is a conjugate word. So this is actually two words. This is actually the words je aime. So we can notice that we have 4 words in the French language of this sentence, and we have 3 words in the English translation. Our encoder is just going to be an RNN, and it's going to have these inputs. This is going to be x0, it's going to be x1, it's going to be x2, it's going to be x3, and similarly, our decoder is going to have these 3 inputs, x0, x1, and x2. And there's also going to be a start of sentence token and an end of sentence token. But let's ignore these for now, just for the purposes of this diagram. But they are there, and they do matter. And these are going to be the time steps at t equals 0, 1, 2, 3, and for the decoder, t equals 0, 1, and 2. This is a simple RNN, and it takes in the first input. So it's going to take in x0, which is equal to je, and it's going to take a hidden state, h0, which is just initialized to be the 0 vector. It's going to produce some prediction. We don't actually care what this prediction is. because for this encoder, we're not trying to actually generate the predicted output. We're just trying to learn the information about the sentence. Okay, and then we continue on, and this outputs a hidden state. It makes a prediction. Let's call it y hat. And we go through each of these time steps. X1 is M, and it produces a hidden state H2. Here we do X2, which is les. And another hidden state, H3. Finally, we get to X3, which is chien. And it produces the final hidden state, which is H4. We will call this HE. So this is the final hidden state of the encoder. And we would also have an end of sentence token and a start of sentence token, but we're just going to ignore them for now for the purposes of this demonstration. Okay, now the decoder is going to do a similar thing, except this time we're actually interested in what the output is. So we're going to have X0 goes into the RNN cell, which is equal to, well, it should be the start of sentence token, but let's say we start at I. We start at the first word. The hidden state, H0, what we want to do is we want to use the information from the encoder, and we want to use it in our decoder, because otherwise, what was the purpose of having an encoder in the first place and passing our French sentence into it if we're not going to use that information in the decoder? We're going to use the information from the encoder. Eventually, we're going to use the outputs, but for now, just as a starting point, we're going to only use the final hidden state from the encoder. So we're actually going to initialize our initial hidden state to be the hidden state from our encoder. So this hidden state actually gets passed into the decoder as its initial hidden state, which means that we have the hidden state information, which essentially is the information that the RNN encoded from the French language sentence, and that's going to be inputted into our decoder. We're going to use the information from our encoder to help us produce our output with our decoder. As a starting point, we're just going to take the final hidden state and input that into our decoder. But later on, we're actually going to use all of these outputs when we look at doing cross-attention. And then we proceed as usual. So we have a hidden state, we have an output. This time our output matters. So at time step t equals 0, we want to predict the next character. So we're going to have an output y hat, and we're going to expect that our output is equal to x1, which is love. RNN is going to make a prediction. It's going to make an output. Now, we don't know whether it's going to be the correct output or not, but we want to evaluate it against the correct output, which is going to be the word at the next time step. So we would hope that our prediction is love, but it may not be love. It may be a completely wrong prediction. And then we're going to go in and we're going to pass in the next word, which is love. And we're going to make another prediction, y hat. And we're going to hope that our prediction is equal to the next word, which is dogs. And so then we're going to get another hidden state. And then, we're going to get x2, which is dogs. And we're going to make one more prediction, which I'm going to put over here. And we're going to hope that it's equal to, the end of sentence token. So we're going to hope that our final prediction is the end of sentence token. So, or if you prefer, this can just be a period instead of an end of sentence token. And we're also going to produce a final hidden state, which doesn't really matter. So that's the basic structure. Everything is pretty much the same as the RNNs that we trained before. This time we're just chaining two RNNs together, and we're using the output from the encoder RNN in the decoder RNN. And that's the basic structure. So that's what we're going to be looking to build. I hope that diagram was helpful, and I hope that it is illustrated the architecture that we want to build, and you're able to conceptualize it and visualize it somewhat. Now we're going to get into the code. We're going to start with the code from the last video where we learned how to generate names in different languages. So if you haven't seen that video, I highly suggest that you watch part 2, because without the first and the second videos, you're going to have a hard time understanding this video. So we're going to start with this code, and I'm just going to copy a bunch of code that I've already written. And this code is just for reading in and processing the data. So I'm not going to spend time going through and explaining the code. If you're interested, then I encourage you to walk through the code and make sure that you understand everything that's going on. Okay, so I'm just copy and pasting the code that we need to read in data. And convert them to pairs. Okay, I might need to import regex. All right, so that's just some simple code to read in the data. And once we've read in the data, let's take a look at exactly what we're working with. So this data set is a data set of English and French pairs of sentences. So for example, if we scroll down a bit, you can look at this sentence, I saw you. In English and in French, it is translated to je vous vis. So let's now, the first thing that we want to do is we are actually going to take these sentences, and because there's many of them, we're going to cut our data set down to a smaller data set that is going to be easier to work with. So I'm actually going to copy some code here. And what this code is going to do is we're going to filter sentences that have a max length of 10 words, and only sentences that start with these two words. So we're going to look for sentences that start with I am, he is, she is, you are, and so on. So we just have this simple function which goes through every pair, and it checks that the English sentence is has less words than the max length, and the French sentence has less words than the max length, and the English sentence starts with any of these prefixes. And we're going to just do that to our data set. So let's do that now. And we get, okay, now we have approximately 11,000 sentences that we're working with. So that's a lot more manageable than we had before. Now, another thing I'm going to do is, because our input is going to be the French sentence and our output is going to be the English sentence, I'm just going to reverse these. So I'm going to go so now we're going to have French and then English. Okay, cool, simple enough. We want to encode our data into a numerical format. So before, we were encoding on a character level. We were encoding every single character of the word. So every single letter would get encoded into a numerical representation, into an index. Here, we want to do it on a word level. So we're actually going to build a helper class which is going to help us to take all of the vocabulary and create indices for all of the words in our English, in our set of English sentences and our set of French sentences. Firstly, we want to define a start of sentence and an end of sentence token. So our start of sentence token is 0, our end of sentence token is 1. And all of this code is no longer going to be applicable to us. So I'm going to remove it. And we're going to have to start brand new. So we're going to create this class, call it lang. And it's going to have a couple of properties and functions that are going to be useful. So the first thing is we're going to give it a name. So because we're going to have English and French, we want to be able to differentiate between the two. We need a word lookup table. We need a mapping from each word to the index, and similarly for each index to the word. So we're going to need a index to word mapping, and we're going to need a word to index mapping as well. Okay. And we're also going to keep a count of the number of words. Cool. All right. So let's start with that. And then we're going to want to be able to process every single sentence in our list of pairs. We're going to have to process each sentence, and we're actually going to have to go through each word in the sentence, and for each word, we're going to need to add the word into our vocabulary. So let's write a function first to add a word to our vocabulary. So let's say we have a given word. So given a word, we're going to check if that word is already in our index. If it is, then we do not need to add it into our index, and if it's not, then we do. So if word in self dot word to index, then we pass. Well, let's do it like this. If word is not in self dot word to index, then we're going to have to add it in. So we're going to take the number of words that we already have, and we're going to just add that into the next index. The index of this word is going to be self.n_words plus 1, and then we're going to do self.index to word at this index is equal to the word, and self.word to index at this word is equal to that index. And we're going to add 1 to the number of words. Okay, let's start with this and see how this works. So let's go English is equal to lang of English. And now let's add some words to our class. So if we take a look at the index to word mapping of our class, it's empty right now. Now let's add a word. So ing.addWord. Hello. Let's add the word hello. Okay, and now let's take a look at our index to word. And let's take a look at our word to index. Word to index. And let's take a look at the number of words. Okay, let's add another word. So let's add the word hello, and let's add the word chocolate. Okay, now let's take a look at our index. All right, looks good. Now what happens if we try and add a word that's already in our index? Let's try and do that. And nothing has changed. Okay, so this looks really good. We're going to add another property to our class, which is going to keep track of the count of each word. So let's do that. So that way we know how many times the word has shown up in all of our sentences. So what we're going to do is we're going to go, if it's the first time that we're seeing this word, then self.word2count at the word is equal to 1. Otherwise, self.word2count at that word is, we add 1 to the count there. So let's take a look at that. So we're going to add the word hello, and we're going to see that it's here, and we're going to take a look at the count of hello is at 1. Let's add hello again, and now let's take a look at the count, and it's at 2. Okay, great. So it looks like our class is functioning as we want. Now what we need to do is we also want to be able to take an entire sentence, because our pairs come in sentences. So we're going to need to take in the sentence. And now we're just going to split up the sentence into words. So for word in sentence dot split by white space, we add each word in the sentence. And that's all. So now we're going to create our two classes. We're going to have a class for the French language, a class for the English language, and we're going to go through every single pair, and we're going to go English sentence, French sentence, let's make sure we're English sentence, let's make sure we're getting everything here. Okay, looks like I got the order mixed up here, so it's just going to be like that. And let's take a look now. English sentence, French sentence. Okay, cool. Everything seems to be looking good there. So now let's just go ahead and process the French sentence in our French vocabulary. Okay, and now let's take a look at everything here. So eng.word2index has all the English words. Word2index has all the French words. Cool. Let's get rid of that. English.word2count has all the English words. France.word2count has all of the French words. Okay, I'm pretty confident that everything is working as expected. And you can see that there's a lot more variety of words in the French language than in the English for these sentences that we have. So that's an interesting observation to make. Okay, cool. So now that we've created our vocabulary, we can use this to encode our sentences. But before we do this, I forgot one thing. We also want to add our start of sentence token and our end of sentence token into our indices. So we're going to need to add start of sentence 1 and end of sentence. Let's do start of sentence 0, end of sentence. Oops, this should go here. And then this should go here. 0 and 1. Okay, so we want to ensure that our start of sentence and our end of sentence tokens are in our vocabulary as well. So now let's check that. Okay. All right, we're good now. So now let us encode. We're going to encode our sentences using this. So what do we need to do? Let's take an example sentence. So we have a French sentence and we have our English sentence. Okay, let's work the French sentence first. C'est un représentant accrédité du gouvernement canadien. So all we need to do to encode the sentence is we need to convert every single one of these words into an index. So all we need to do is we need to go for a word in a sentence. We're going to go France.word2index word for word in French sentence dot split. Okay, so now we've converted all of the words into their index in our vocabulary, and all that we need to do is we need to go indices is equal to this. We're going to append a end of sentence token, which is that, and we're going to insert a start of sentence token, and we're going to convert this to a tensor. So this is what we end up with. Cool. And we'll call this sentence 2 indices. And we want to specify which language we're working with. And so got this. All right, let's try this out. Sentence 2 indices of our French sentence. our French language, and our English sentence, our English language. Okay, looks like it's working. Great. Now we're going to define our neural network. And what we're going to do is we're going to have two recurrent neural networks. One is going to be for the encoder, and the other is going to be for the decoder. So let's create two neural networks. The first one we're going to call the encoder RNN, and the second one we're going to call the decoder RNN. Okay, so we learned in the second video how to create this RNN from scratch. So this is great, but for simplicity's sake, we're just going to replace this with the built-in GRU that is offered in the Torch library. So another thing that we're going to do is we're going to use an embedding. If you're not familiar with what an embedding is, I encourage you to read through some documentation on embeddings and how they work. So simply put, it's a way to map words into n-dimensional vectors and encode some useful information about each of those words. So what that means, practically speaking, is the word hello would get encoded into some vector representation, which might be a vector with the values 1, 5, 7, 9, 10, 11, and -17 as an example. So there is a nice built-in embedding class in Torch which we can use for this purpose. So we're going to call this self.embedding is equal to nn.embedding, and it's going to have the dimensions of our input size, and its output is going to be the hidden size. So this means that our input is going to have an input size, and then it's going to get embedded, so it's going to come out with a hidden size dimensional vector, and that's what's going to get passed into our RNN. So that means that we're going to have an RNN, but we're going to use a GRU as our RNN. So it's going to be nn.gru, and the input is going to have a hidden size, and the output is also going to have the hidden size. Okay, and we're going to do batch first is equal to true. Okay, and then we're going to have a dropout layer. If you're not familiar with what dropout is, again, I encourage you to take a look online at some resources. All that dropout really is we turn off a percentage of the nodes in our given neural network layer so that it allows the neural network to ensure that it uses every single node, because otherwise the neural network might just ignore some of the nodes and have them always set to 0. And now we no longer need a softmax layer because we don't actually care about turning our output into a prediction, because we're just encoding information. So that's what we have. And so what happens is we no longer need to combine things. What we're going to do is we're going to take our input and we're going to pass it into our embedding. So embedded is equal to self.embedding of the input. And then we're going to now just take our input and our hidden, and we're going to pass it into our RNN. So output hidden is equal to self.gru of our embedded input, and the previous hidden state. And then we're also going to use some dropout here. And that's it. So this is our neural network. Super simple. And yeah, that's really all that it is. Not much that we're going to be changing here. We're going to make one small adjustment here. This is because our GRU requires an additional dimension. We're going to just make this change here. So yeah, that is pretty much everything. We're also going to our output size is just going to be the same size as our hidden, so we no longer need that. We're going to add a dropout probability, which is initialized to 0.1. So that's going to be required as well. And that's our encoder. It's very simple. Now let's move on to our decoder. So let's make sure that our encoder is actually working as we expect it to. Let's add some print statements here. Okay, and then let's do output size, and we'll do hidden size. So I really like to print all of the shapes at each step in the neural network so that we can see everything that's going on. So let's initialize our encoder first. So encoder is equal to encoder RNN. So what is our input size? Well, because we're encoding the French language, our input size is going to be the number of French words. Okay, and our hidden size we can define as we like. I'm going to choose 128. And we want to make this adjustment. Okay, so we have our encoder. Now let's take our French sentence. Let's convert it into a tensor. Tensor is equal to sentence to indices. Sentence to indices of the French sentence. And this is our French tensor. Okay. Let's get our hidden state. Okay, hidden is just zeros. All right. Now let's see what happens when we pass this into our neural network. Okay, we no longer need to put in the language here. So let's redefine that. Okay, let's see what happens. Encoder of our French tensor. right, we're going to need to, yeah, we can just pass in the entire tensor at once. So let's see what happens. Oh, right, and of course we need to add our hidden as well. So input and hidden. Index out of range. Let's see. Because we have the start of sentence and the end of sentence token, we actually need to make sure that we initialize the number of words to 2 here. Yes, of course. I can't believe I forgot that. Okay, so let's rerun everything from scratch. Okay, so there was another small mistake here, which I just realized, is that we actually want the index to be the number of words because we start indexing at 0. So, okay, now everything should work. Okay, and it does. So, okay, we can see what we get here. We should get the same number of outputs as we have inputs. So that seems like what we get. So we get output 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we should get a single hidden. Okay. And we do. So this is our encoder. And now what we're going to do is we're going to build a decoder. And it's going to also just be a basic RNN, just like our encoder. However, we want to actually break it up step by step, not pass in the entire sequence at once like we did in our encoder. We want to iterate through every single time step and do it one by one, because later on we're going to be adding cross attention, which is going to require us treating every single time step individually. So let's go ahead and code that up. So let's start with what we had with our encoder. So everything is going to start off the same, except we're going to do two things. Instead of one forward step, which goes through the entire sequence, we're going to do a forward step. So we're going to go through every single time step. We're going to pass our input and our hidden through our RNN at each time step. This hidden we're going to rename as so this time we do actually need to know what our output size is going to be. Yeah, we're going to take in the hidden state, but the hidden state that we start with is actually going to be our encoder hidden state. So we're just going to take the hidden state from the encoder. So for this one, we're going to need our English tensor. So let's go English tensor is sentence indices of our English sentence in English. Okay, this is our English tensor. Size. This is the length of our sequence. So sequence length is equal to English tensor dot size is equal to our input dot size at 0. Okay, so now we're going to go through for I in range of our sequence. Square length. All right, so we're still going to embed it. So embedded is equal to self.embedding of the, so nothing else changes here. We still have a GRU. We still have dropout. Self.embedding the input. For I in range of sequence length, we're going to pass the embedded at, so we're going to have to take each one of these i's. This is our input, and this is our hidden. And here is where we're going to get the output and the hidden from the input and the hidden. And so we're going to go input hidden is equal to, output hidden is equal to forward step of this, and we're going to need to collect all of these outputs. So how many outputs are we going to have? Well, we're going to have sequence length, and we're going to go outputs at is going to be equal to the output. Okay, so this is what it should look like. Okay, and we need to initialize our hidden. So just to recap what's going on here, we, instead of passing the entire sequence into our RNN, into GRU, and just having it process the sequence itself, we're going to go through the sequence at each time step by step. Okay, so that's what's changing between the encoder and the decoder. So they're essentially the same. I've just chosen to unravel it and pass along each step one at a time, because we're going to need this later on when we do attention. It's going to save us a lot of trouble if we do it this way. So in order to do that, we're actually going to have to build up our outputs ourselves. So what we do is, we initialize our hidden state to be our encoder hidden state that we got as an output from our encoder. Then we create this tensor to hold all of our outputs. So it's going to have a output for every single one of the time steps in our sequence, and it's going to have a hidden size dimensionality for each output. Then what we do is, in our forward step, we pass in just the input for that specific time step that we're at. We get the next output and the next hidden for that time step, and we add it to our outputs tensor, and then we return all of the outputs and the final hidden state. Okay, so I don't know if this is going to work, but let's give it a try. And we no longer need the init hidden because we are passing in the initial hidden state. And we want to return the output and the hidden here. Okay, let's see what we get. This is probably not going to work on the first go, but let's give it our best shot. So let's add some of these print statements here. So we want the input size, we want the embedded size, and we want the output and outputs size and hidden size. And this was actually, this should have been here. Oops. Anyways, it seemed like things worked anyhow. So, and maybe we can even print the output size, output dot size. Sorry, we can output it here. I know that's a lot, but let's let's also print I. Okay, I know that this is quite a bit, but let's try our best and see if it works and what we get. So let's initialize our decoder. All right, so our decoder is equal to the decoder RNN. And our output size is equal to I don't think we need both the input and the output size, so maybe we'll leave this as output size, and here we can just go output size. So hidden size, output size, dropout P. Okay, and then let's go decoder of, so we need the input, which is the English tensor, and we need the hidden, which is the hidden from here. So let's save this as encoder hidden. Okay, so let's do that. Okay, and now we can use that here. And we got an error just like we expected. Okay, hidden size has to be self.hidden size. Okay, that seems fine. Forward step is not defined. Maybe I have to define it as self.forward step. That would make sense. And I made a stupid typo. Okay, and I forgot a return statement. I'm just making all kinds of mistakes. I guess that's what happens when you try and code in real time. But I'll edit this out in post-processing, so it'll look like I didn't do anything wrong. Wow, and surprisingly enough, it did not work. This should be shape. I don't know why I put size in here. Okay, so input size, embedded size, output size, outputs size. Okay, output size is 1 and 128. That is not good. So something went wrong here. Did I print? Okay, let's try this again. Okay, maybe it worked. Are we getting different outputs each time? Yeah, it looks like we are. Okay, well, it looks like it's working. So this seems pretty good to me. So let's just recap what is going on here. This is the same as this. The only difference is instead of passing in the entire sequence, so this input here is 10 has 10 dimensions in the first. This has 10 values in the first dimension, okay, because there's 10 words in the sequence. So instead of doing that, what we did is we looped through every single one of the words in the sequence and we passed just that word into the RNN to get just that output. If you pass in an entire sequence, the RNN class is smart enough to process the entire sequence and to give you all of the outputs. But if you give it just a single value, it's only going to give you that one output. So that's what we did. But essentially, this is the same as the above. And the only difference is instead of initializing a empty hidden state at the beginning, like we did up here, we initialize the hidden state to be the hidden state from the encoder. So now let's clean this up a bit, remove some of this junk that we don't need. We've already essentially done this up here, pass an example through our neural network. I'm just going to go ahead and define we'll do this, and then let's start putting these all together. And then we can bring this down here to pass an example to our neural network. So this is the encoder part, and the decoder part is here. Okay, so now we just need to calculate the loss, which we're going to do. So we've got this, and we're passing the example through here, through the encoder. We get the hidden state, then we pass it through the decoder with that hidden state, and we're done. Let's comment these out. Okay, now we want to calculate the loss. So we also have to take our outputs and we have to convert them into probabilities for the next word. So we can't just take our outputs as they are. We need to have a linear layer to map them to the output size. So we have to take our outputs from our RNN and we have to pass them through a linear layer to give us a vector that has the same dimension as the number of words in our English vocabulary. So we're going to need one more linear layer here, and we're going to need a softmax as well. So we're going to call this output to output, and it's going to be a linear layer, and it's going to go hidden size to output size. So going back here, we can go outputs equals nn dot linear, outputs equals self dot o2o of the outputs, and we also are going to need to take a softmax. So outputs equals self dot softmax. Want to do that. Okay, let's try this now, see what we get. Okay, that looks pretty good. I think that's what we want. Yeah, this looks great. All right, so now we can calculate the loss here. So just to explain what happened, we have, when we pass it through our RNN, the outputs are going to have a dimension of the hidden size. However, we want to predict the next word, and there are 2,991 English words. So we need to blow up our 128 dimensional hidden output from the RNN into a 2,991 dimensional vector, and then to turn it into a probability, we do log softmax on it. So that's all that's going on there, because we want to convert our output into a prediction that we can use to decide what is the next word in the sequence. Our targets is equal to our English tensor from 1 to the end. So these are our targets, and we want to check whether our outputs okay, we can just do this to everything except for the last token. That's what we want to evaluate against. So if we were looking at the first prediction, outputs as 0, we want to evaluate this against targets as 0. This is our criterion. Let's now go outputs as 0, targets at 0, and we get a loss of 7.7833. Which is correct, so that's fine. And we want to do this for the entire input sequence. For I in range of sequence length, we're going to go loss is equal to criterion of we want to go sequence length -1. We want to go loss is equal to the criterion of the outputs. You know what? Let's do this. Target equals English tensor up to the end. Outputs we can keep as is. And we can go the loss at the current time step is equal to the outputs at that time step, and the targets at that time step, what is the difference there, and then we can add it up, and we can go print of I, print of loss. So let's make sure that's all going. I'll go total loss equals 0. Maybe we should normalize the loss. So let's go, yeah, let's do that. So the total loss is 0. We calculate the loss at each time step, and we add that to the total loss. And then let's see what the total loss is. So let's do this instead. Okay, so that is our total loss. And then we're going to divide our total loss by sequence length minus 1. Okay, so this is our total loss. So it looks like we've been able to pass an example through our neural network and get the loss successfully. Now let's put this into our training code. To get a random example, all we have to do is just take a random sample of the pairs. So we probably don't need this function anymore. We do need this. So let's take all of this in here. Okay, so let's get a random example by going sentence equals random dot sample of pairs, comma 1. Let's make sure random dot sample of pairs, comma 1 has 0. Okay, cool. So this is how we get a random example. And now we're going to go here and we're going to initialize the hidden state. And we're going to get our tensor. And then we're going to pass it through our encoder and get the output and the encode and the hidden state from the encoder. Then we're going to do the same for the decoder. Alrighty. So similar idea. We get the English tensor by converting the sentence to indices. Then we get the outputs and the hidden from the decoder, and we pass in the encoder hidden as the initial hidden state, and we're going to zero the gradient. All right. And then we're going to calculate the loss. So everything looks similar here. Let me just okay, we can define this out here somewhere. Okay, let's throw this in here. So the sequence length is that, the targets are that, the total loss is 0. Maybe let's not call this total loss. We'll just call this loss, and we'll call this L. We'll go loss plus equals to L, loss, and loss dot backward. So for P and encoder dot parameters, we'll do this. And then for P and decoder dot parameters, we will do the same. Okay, let's give this a try. RNN.0grad. Okay, we're going to do encoder.0grad, and we're going to do decoder.0grad. Oh, these got mixed up somehow. Right, the order, of course. Okay, let's try again. Name to target. Where's that coming from? Okay. That was some old code we forgot to delete. Now let's try again. Okay, it seems like it's running and not throwing an error. So let's see what we get as an output. All right, so we made one small mistake. We have to use a different variable for this iterator here because we're already using I. So let's fix that. And now we can run everything from the beginning. Okay, and our neural network seems to be training. So let's give that some time and then let's check back in and see what the results look like. So one change that I forgot to do that we will want to do before we want to move forward to completely training our neural network and start making some predictions is in our decoder, you'll see that we're only ever generating as many outputs as our sequence length. So this is assuming that we know what the answer is. The way that we have our neural network set up right now, it works perfectly fine for training because we actually pass it the true input. So we pass it the true English sentence that we want to try and generate, and we evaluate it against the true English sentence. So that's why we only iterate through the sequence length. However, if we don't have the right answer and we want to use this in an inference mode, we don't want to have this restriction. We actually will want to iterate and generate outputs all the way until the max length and have the neural network decide when it wants to output it an end to the sentence. So we should make that adjustment here. So what that means is instead of just taking in the input, because in an inference setting, our input was usually just going to be the start of sentence token, or it might be just the next word that we've predicted. So our input is typically just going to have a length of 1. What we want to do is instead pad our input. We want to pad our input all the way until the max length. So what we're going to have is we're going to take our input and we're going to create this padded input, which is just starting off as a vector, as a tensor of zeros. So we're just going to fill it with our start of sentence token. It's going to have the max length plus 1. It's going to be a torch tensor, of course, and we're going to fill it with our start of sentence token. Okay, and what this does is we have just an input of zeros. And now we want to fill in the input with our actual input. So here what we're going to do is we're going to iterate through the sequence. And we're going to assign the input, the padded input, to be equal to that actual input. So now we have a tensor, which is the length of our max length, and it's going to have all of our input, and then the rest of the tensor is just going to be filled with start of sentence tokens. Okay, and now what we want to do is we want to pass our padded input through the embedding. And here, now we want to generate outputs for the entire max length rather than just the sequence length. So now we're going to go, the output is now equal to the same length as the padded input. So max length plus 1. And then again, we go max length plus 1. And that's it. Now we've generated a max length number of outputs. So when we don't have the true answer, we can generate as many outputs as it takes until we reach the end of sentence token, or if we don't ever reach the end of sentence token, then we just stop. We cut it off at the max length. So let's give that a try now and make sure that it works. Okay, it seems to be working. Let's just check our outputs at this stage. Good, we have 11 outputs. Okay, everything looks good on that front. Okay, now let us train our neural network. Okay, everything seems to be working. So let's check back in after it has had some time to train and see what kind of results we get. All right, our neural network has now finished training and looks like it's done pretty well. So let's take a look at the plot of the loss, our learning curve. And we can see that the neural network is slowly decreasing the loss. So that's good. There's obviously a lot of room for improvement here, but don't worry because we're going to make a lot of improvements to this neural network. And what we want to do now is we want to have the ability to use this neural network to make predictions. So we want to give it a sample French sentence and have it output a English translation of that sentence. So what I've done is I've taken an English sentence, which is, I am scared of big dogs. So this is going to be our English sentence. And I've used Google Translate to translate it. And the translation that it came out with was this. J'ai peur des gros chiens. Okay, and now what we want to do is we want to use our neural network to try and translate this French sentence. So the first thing that we need to do is we're going to need to use our text processing functions that we wrote at the beginning in order to normalize our text to convert it to the format that we used in the model. So we're going to use our normalize string function, and we're going to do that to our French sentence. Okay, and now to make predictions, we're basically going to just steal the code here. And we are going to do this. Okay, so we have our French sentence and our English sentence. We don't care about the gradient. We need an initial hidden state to start with. And what else do we need? So we can encode our French sentence as a tensor. Okay, wonderful. And now we get our encoder hidden state, and this is going to get passed into our decoder now. And for our decoder, the decoder is what's actually going to generate every single word in the sentence. What we need to do for our decoder is we need to start it off so we don't have an actual English tensor. Well, we do, but we're not going to use it. So we can remove that. And we're just going to pass in the encoder hidden and the English tensor. We don't want to pass in the English tensor because we want it to try and predict the answer by itself. So we just want to start it off with an initial input, which is just going to be our start of sentence token. We take our start of sentence token, which is just 0, and we convert it to a tensor. Okay. So this is our input. All right. And now we can pass our input in and we will get a bunch of outputs. So let's do that and see what we end up with. So we get an output, we get multiple outputs, but really we only care about the first output. We take the first output. So the first output is our prediction for the next letter in this word. The word that was predicted by our neural network for being the first word in our English sentence is going to be, we take the highest probability output. So we do, we can say our output is equal to outputs at 0. And we can say our, we can take output.top k. Okay. Okay, it predicts the word at index 2. Our predicted index of our first word is the word at index 2. Take that index, and we get that the first word that it predicts is the word I. So that is actually correct. All right, and then what we do now is we take our next word is I. We take our next word and we add it to our English sentence. So our English sentence is, the start of sentence token. Okay. Well, we'll just say, okay. And then we'll append the next word. So our sentence so far is just I. Okay, so now what we're going to do is we're going to take the next predicted word and we're going to use it as the next input. So we're going to pass it through our neural network once again. We don't need this either. And we're going to go, I'm going to take the IDX and we're going to pass that as our input. And we're going to take the previous hidden state and pass that in as the hidden state input. And we're going to get the next predictions. And we're just going to take the prediction for the next word, which is the first prediction. Okay, and we're going to do the same process. Okay, and this, and this, and this, and we're going to get I. Let's continue and see what the entire input that we get is. So we're going to put this in a for loop. So let's start from the top here. So in the decoder, we go English sentence is this. The English sentence is that. This is our initial input that we're starting with, and we're initializing our English sentence as the start of sentence token. Now, what we do is we go for I range of max length plus 1. So we're gonna go all the way until we reach our max length. We're going to pass our input, our current word, into the decoder to get the next word. And once we do that, we're going to take the outputs, and we're going to take the next predicted word, and we're going to append it to our sentence, and then we're going to use it as the next input. So, oh, and actually we should have been using the index here, because this is the next output. So let's just run this again from the beginning so that we can make sure that we're getting the right thing. Okay, so yeah, we are getting the correct prediction, I am. Okay, wonderful. So maybe we'll go predicted index, and we'll say predicted index. Okay, and then we will set the input is equal to the predicted index. Okay, and what that does is that means that in the next step, the decoder is going to take the previous predicted index from the previous output and use that as the next input. Okay, and that all looks good to me. So let's give this a try. Okay, and let's see what our English sentence looks like. I'm not, I'm not, I'm not. Okay, that doesn't look great. We should be updating this hidden state every time. So we're going to initialize our hidden state here as the encoder hidden. And then here we're going to use the hidden state. So if you're not careful, it's super easy to make these little mistakes as you see me doing. So try not to copy my example and try to make sure you pay attention to all of the details. I'm not are all the ones a good. Okay, so another thing that we want to add is that if we ever predict the end of sentence token, then we want to stop. If it is the case that our predicted index is equal to the end of sentence token, right, then we want to break. All right, so we want to add that. Let's wrap this in a function now. All right, so find predict, and we're going to take a French sentence, and we're going to we're going to encode our French sentence by just passing it through the encoder. Okay, then we're going to take that hidden state that we encoded, and we're going to initialize our English sentence as just the start of sentence token. And we're going to initialize our hidden state as the encoder hidden state. And we're going to bring this in. And we're just going to predict the next character and then use that prediction as the input and pass that into our RNN again to predict the next word, and so on and so forth until we've formed a complete sentence. Okay, and then we are going to return the We probably don't actually have to put the start of sentence token here in the English sentence. So we'll just leave that because that's already a given. And we will join everything and return it to form our English sentence. So now let's call this on our initial French sentence. I'm not a very good at all the one R. I'm not a very busy's a good at all. I'm not a very good. Okay, so we're getting some translations that aren't exactly correct translations, but let's see how it performs on some of the samples that it's seen. So let's do this. Let's take a random sample of our data. So I'm just going to take 10 random samples. Random dot sample of pairs. Okay. Then I'm going to go translation is equal to predict of the French sentence. Okay, and then I'm going to print the French sentence is equal to the French sentence. The English sentence is equal to the English sentence, and our predicted English sentence translation is equal to translation. So let's do this for some random samples and see what we get. Okay, so for the sentence "Il vous attendant," which translates to "they're waiting for you," we get "they're all the one of all of the one of all." And okay, let's not. If it's the end of sentence token, let's not add that to the word because that's a given. Okay, let's do this one more time. Okay, je ne suis pas alcoolique. I'm not an alcoholic. I'm not a good, not, okay. Nous sommes prudents. We're careful. We're all happy. We're not doing the best, but it seems like we're making some sort of somewhat intelligent prediction. So I'll leave it there. We were able to use our neural network to translate French sentences, albeit not the best, but we're going to improve on that and try and make our neural network better. I think we did a pretty good job building an entire sentence translation sequence to sequence neural network is not an easy task at all. I just want to recap everything that we've done thus far. Okay, so what we did is we imported the data, which was a bunch of pairs of English and French sentence translations. Then we filtered them out to only work with a specific subset of sentences that started with these specific English prefixes. That just made the problem easier to solve and made the data much smaller. Then we developed a way to encode all of our text data into numerical tensors that could be processed by our neural network by essentially just translating all of the words to an index and putting them into a tensor format. Okay, then we defined our neural networks. So we started with an encoder. The encoder was simply the GRU RNN that we took from the previous video. And our decoder is also simply a GRU that we took from the previous video. The only thing that we changed is we actually explicitly iterate through all of these steps in a for loop one by one. We also ensure that we generate an output with a fixed length rather than using the length of the actual true output, because when we're making a prediction, we're not going to know what the answer is. Essentially, we just took the GRUs that we learned how to build previously, and we use those as both our encoder and our decoder. So so it's pretty cool how the GRUs that we learned to make in the previous videos for doing a simple encoding task, when we had to try and predict the language of origin of a set of names, and a simple decoding task when we tried to generate names with a specific language of origin, how we were able to take those and put those together to perform a sequence-to-sequence translation task, which takes a French sentence and translated it into an English sentence. Then we simply trained our neural network by creating a training loop. And we finally wrote a function to be able to use our neural network to make a prediction on any input that we give it. That's everything for this video. If you watched to the very end, then leave a comment letting me know. I know these videos are long and technical, so I appreciate you sticking through all of the code and all of the machine learning theory. If you found this video interesting or useful, then I encourage you to subscribe to my channel, leave a like, check out some of my other videos. I'm going to be making a lot more machine learning related videos and tutorials on my YouTube channel, so stay tuned for those. And thank you so much for watching. I'll see you in the next video. Take care.